Hello, welcome to the last day of class. We're talking about different methods for detecting black holes. I'm going to talk about this one method using eclipse timing variations of triple star systems to detect black holes. So a triple star system is a hierarchical triple where you have a close binary that is at the center of the binary, and you have a wide tertiary orbiting it. 25% of multiple star systems are in these kind of multiple configurations of triple star systems. The minimum period ratio for these systems is around 5 to 10, such that the orbit of the orbital period of the tertiary is never shorter than this. Otherwise, the system would destabilize. And for most systems, the mass of the tertiary is less than half of the mass of the inner close binary stars. A famous example includes Algol, which is this wonderful looking image from interferometer showing the different components of the Algol system at high resolution. So the eclipse timing variation technique is more or less where one observes an eclipsing binary. And if you were to assume a purely Keplerian orbit, you would have the mid-transit time occurring at regular intervals. And if you have the effect of a perturber, the influence of a perturber in the system, there could be a number of effects that cause this, from tidal interactions like travel time variations and dynamical effects that result in the mid-transit time varying from eclipse to eclipse. So the ways to kind of visualize this is that it causes a periodic variation where these are transit curves of an exoplanet system that is undergoing transit time variation, where you have the nominal curve assuming a linear ephemeris, a purely Keplerian ephemeris at the top, then you have this shift where you're going late, then early, then late again, then early. But it's periodic, where in a sense where it actually repeats itself. You actually go back to the nominal light curve at some point. And so this is due to, as I said, a combination of effects. So you have the light travel time effect, where you can kind of imagine that as the tertiary is orbiting the close binary system, the close binary stars, is that its gravity is actually moving the barycenter, and thus the source of light observed from between the observer and the star system is actually the distance actually growing or shrinking. And so the amplitude of this effect is actually on the order of minutes. It's actually very small, and that is proportional to the our mass function, which, as you can see at the top. And the key thing to note here is that it's a function of the mass of the tertiary and the combination of masses from the close-end binary and the tertiary, as well as the inclination and so major axis, the close-end binary, and so on. But all those things staying equal, the main influence here is going to be that you have the period of the tertiary that is actually going to be that's actually going to be inversely proportional to the amplitude. So the longer the period, the shorter you can, the smaller the amplitude that you are going to have. And so the consequence of this is that for periods shorter than, say, some tens of days, you are not going to have the effect is not going to be nearly as detectable. Another thing to note here is that the eccentricity is also a key factor here. That this effect is stronger for circular orbits. The other effect is that you have is on the dynamical interactions between the different bodies in the system, and this is a combination of different orbital elements of both the Titan binary and the tertiary. But it can be simplified just in terms of the period of the close-in binary and the tertiary, where we can see that you have a square dependence on the period of the primary, such that for periods less than 1 day, it makes the detection of this dynamical effect more difficult. So we can see here that there's the dependence is actually weaker on the period of the tertiary for the light travel time effect than is the dependence on the period of the close-in binary. So that on more systems, you're going to have the light travel time effect detectable, and the dynamical effect is going to be less detectable. And it's going to be pretty much impossible for periods less than 1 day. And to give you a kind of idea of that, how those are distributed, is that for the majority, so this is a plot of eclipsing binary systems, triple systems observed by Ogle. And you can see that for the vast majority of systems that they are above this line here, which is the amplitude of light travel time, where this is the regime in which the light travel time effect is detectable. But this kind of diagonal line here showing the regime in which the dynamical effect is detectable, eschews the vast majority of the objects of the systems. And you can notice here that this is actually on the converse of that, there's actually a small number of systems, a couple of systems, where the dynamical effect is measurable, but the light travel time effect is not measurable. So what these kind of, how this analysis is done is that you fit your model. In this case, this is a light travel time effect only model here. That's this green line here, against the observed minus computed light travel time. So you have your observed light curve, and you have your computed light curve assuming a purely Keplerian orbit. And so that difference is going to give you the amplitude, the deviation from the purely Keplerian assumptions. And you fit your model according to that in order to get your parameters. So this top panel here on the left side, that is the raw light curve here. And on the right-hand panel, that is these data right here, phased according to the period of the type binary. But what you can notice here is that the model is actually periodic. You have it ending and repeating here within this 2,000-ish day time period. And so you can also fit both a combination dynamical and light travel time effect models here. It doesn't look that much different, but it's more or less periodic. But when you can combine these two things together, you can actually directly infer the masses of the different stars in the system, including the tight end binary. Whereas if you have light travel time only, you can only infer the lower limit on the tertiary, the mass of the lower limit of the tertiary. And so this is for the combination of the two effects for two systems, that you have the mass of the different stars right here. But one thing to keep in note here is that you have the ratio of the amplitude of the dynamical effect and the light travel time effect, which are both less than 1. And so it shows you that even in this kind of optimistic case, you have where the period is 2 days for the tight end binary, 2.5 days, 2.8 days. The dynamical effect is always going to be weaker than the light travel time effect. So another thing to note here is for these systems, these triple systems, and is that the eccentricity of the tertiary is pretty moderate. It's somewhere around 0.3 or 0.4. And so what's selected and all the difference in between the yellow curve and the blue curve, what this author indicated is the reliability of the fit. And so I think what this implies for these systems, if you're going to look for black holes in these systems, is that if there are black holes and they are detectable, is that they have some kind of formation pathway that results in them being on more eccentric orbits. Perhaps the common envelope evolution might not be applicable here due to the higher eccentricities, because that would incur tidal effects and circularize the orbits. as the black hole is formed, if it had any kind of interaction with between itself and the Titan binary. So this is showing the cumulative distribution of the eccentricity, in that it seems to be lower eccentricity, despite what I just said. It seems to be lower eccentricity than what the previous assumptions are for the eccentricity distribution of triple systems. And so one thing to note is that the primary period of the binaries is typically smaller than 1. So that's what precludes the use of this dynamic limit, which is insensitive to periods of 1, less than 1. So what's also interesting is that these data also indicate a triple frequency that is actually increased for close-in systems. Or systems with short binary periods. So it implies that there's some kind of stabilizing effect here with the we have systems that are so close together, but they might actually be less stable if they did not have a tertiary involved. And so one thing you notice is that these tertiary systems have fairly longish periods, and so for the less reliable periods, is that this is actually the limit. Around 2,000 days, actually the limit of some of the observations. And so if you're fitting a period to the a model, the period that you're getting from the model is, if it's your span of observations is approaching or actually less than the actual period of the tertiary, the solution is going to be converging on what the limit is, the time span of the observation. So that's probably an artifact of the artificial boundary of the time span of the observations. And this is this plot again, and this is to show that you have this kind of different unstable region right here in this purple zone, where you cannot have binaries that are too small ratio of the tertiary to the close-in binary, and that you have a good number of these determined systems that have they're purely light travel time, and that the sensitivity is somewhere around 50 seconds. That's kind of your sensitivity limit. And when you look at we'll talk about what that sensitivity limit implies. But when you look at the minimum mass of this third companion for the reliable category, is that you only have a handful that are that have a mass of more than 2.5 solar masses, the theoretical maximum mass of a neutron star. So those would be what you would want to examine more clarity if you wanted to test whether or not they had an unseen component or less light than predicted, lower luminosity than predicted by the total mass of the system inferred from this. So the lowest amplitude here is that you're getting around half a minute. That's kind of the limit of the technique here, and this is compatible with a tertiary period around 1,000 days, which is a lot shorter than what most of these data points, most of the data in this data set have. So it implies that perhaps these kind of small amplitude systems are actually kind of rare. And so this is by the numbers looking at the feasibility of this technique, is that Ogle obtained 400,000 eclipsing binary light curves, but only 1/5 of everything in the data set from this data release at the time of the paper was being written had enough data suitable for eclipse timing variation fits. And out of those 80,000, only 1,000 were identifiable, had an identifiable tertiary. And out of those 80,000, 2 had enough data and the circumstances of the period of the inner dynamical tight dynamical binary had enabled mass determination, but 6 had reliable tertiary lower mass limits larger than the primary and mass around 2.5 solar masses. So these could be where you would want to look just for additional tests to see if there's a black hole. But thank you. That's all I have. And sorry I'm not there. I'll try to show up later for you to participate in the discussion.